Hi everyone, welcome back. In this video, we will understand Kubernetes architecture in a very simple and beginner-friendly way. Kubernetes is a container orchestration platform. That means Kubernetes helps us run, manage, scale and monitor containerized applications automatically. For example, imagine we have a Java Spring Boot application running inside containers. If we want to run one container, Docker is enough. But in real-world projects, we may need many containers, multiple application instances, automatic restart, scaling, load balancing, and deployment management. This is where Kubernetes helps us. Kubernetes architecture has two main parts. First, the control plane. Second, the worker nodes. The control plane makes decisions. Worker nodes run the actual applications. Think of the control plane as the brain of Kubernetes, and think of worker nodes as the machines where our application containers actually run. Now let's start with the control plane. The control plane is responsible for managing the entire Kubernetes cluster. It decides where applications should run, checks the health of the cluster, stores cluster information, and keeps the system in the desired state. Inside the control plane, the first important component is the API server. The API server is the entry point of Kubernetes. Whenever we use kubectl, YAML files, dashboards, or automation tools, they communicate with Kubernetes through the API server. For example, when we say, run 3 copies of my application, that request first goes to the API server. The API server validates the request and accepts it. So in simple words, the API server is the front door of the Kubernetes cluster. The next component is etcd. KD is the cluster database. It stores all important information about the Kubernetes cluster. For example, it stores information about nodes, pods, services, deployments, secrets, and configuration. One important point is that etcd talks only to the API server. Other components do not directly talk to etcd. They communicate through the API server. This keeps the cluster management clean and controlled. In production, high availability clusters, etcd usually runs on separate dedicated nodes because it is a very critical component. If etcd is lost, the cluster state information is lost. So etcd is like the memory of the Kubernetes cluster. The next component is the scheduler. The scheduler chooses the best worker node to run a pod. A pod is the smallest deployable unit in Kubernetes. A pod usually contains one application container, but it can contain more than one container in special cases. When a new pod needs to be created, the scheduler checks available worker nodes. It looks at CPU, memory, rules, constraints, and availability. Then it decides which worker node is the best place to run that pod. So the scheduler does not run the pod directly. It only chooses the node. The actual pod is started by the worker node. The next component is the controller manager. The controller manager maintains the desired state of the cluster. This is one of the most important ideas in Kubernetes. In Kubernetes, we define the desired state. For example, we say, I want 3 pods of my application running. Kubernetes continuously checks the current state and compares it with the desired state. If one pod crashes, the current state becomes 2 pods. But the desired state is 3 pods. So Kubernetes automatically creates a new pod to bring the system back to the desired state. This work is handled by controllers inside the controller manager. So in simple words, the controller manager makes sure Kubernetes keeps running the way we asked it to run. The next component is the cloud controller manager. This component manages cloud-related resources. For example, if Kubernetes is running on AWS, Azure, or Google Cloud, The Cloud Controller Manager helps connect Kubernetes with cloud services. It can help manage cloud load balancers, cloud storage, and cloud networking. So if our Kubernetes cluster is running in the cloud, this component helps Kubernetes work properly with that cloud provider. Now let's move to worker nodes. Worker nodes are the machines where our actual application runs. A Kubernetes cluster can have one worker node, two worker nodes, or hundreds of worker nodes. Each worker node has some important components. The first component is Kubelet. Kubelet is an agent that runs on every worker node. It communicates with the API server and makes sure the required pods are running on that node. For example, if the scheduler decides that a pod should run on worker node 1, Kubelet on worker node 1 receives that instruction. Then Kubelet starts the pod using the container runtime. So Kubelet is responsible for running and monitoring pods on a worker node. The next component is kubeproxy. Kubeproxy handles networking and service routing inside Kubernetes. In Kubernetes, pods can be created and destroyed at any time. Each pod gets its own IP address, but pod IPs are not stable. So Kubernetes uses services to provide stable access to pods. Kubeproxy helps route traffic from services to the correct pods. It uses networking rules like iptables or IPVS to manage this routing. In simple words, Kubeproxy helps network traffic reach the correct application container. The next component is the container runtime. The container runtime is responsible for running containers. Kubernetes does not directly run containers by itself. It uses a container runtime such as Containered or CRI-O. The container runtime pulls container images and starts containers inside pods. So Kubelet gives instructions and the container runtime actually runs the containers. Now let's understand what runs inside worker nodes. Inside worker nodes, we have namespaces, deployments, replica sets, pods, and containers. A namespace is used to logically separate resources inside a Kubernetes cluster. For example, we can have one namespace for the application and another namespace for monitoring. This helps organize resources properly. A deployment is a Kubernetes object used to manage application deployment. When we create a deployment, we tell Kubernetes what application image to run and how many replicas we need. For example, we may say, run 2 replicas of my application. The deployment manages a replica set. A replica set makes sure the required number of pod replicas are running. If one pod fails, the replica set creates another pod. The pods contain the actual application containers. So the flow is simple. Deployment manages replica set. Replica set manages pods. Pods run application containers. Now let's understand how users access applications running inside Kubernetes. Users do not directly access pods. Instead, users usually access the application through ingress and service. Ingress is an entry point to the cluster. It helps expose applications to the outside world using domain names and HTTP routing rules. For example, we can route traffic from app.example.com to our application service. After traffic enters through ingress, it goes to a service. A service provides a stable IP address or stable access point for pods. This is important because pods are temporary. A pod can crash, restart, or move to another worker node, but the service stays stable. So users access the service and the service sends traffic to the correct pods. In simple words, ingress brings traffic into the cluster and service sends traffic to the right pods. Now let's understand the deployment flow step by step. Step 1. We create a YAML file and apply it using kubectl. The YAML file defines the desired state. For example, it may define a deployment with 2 application pods. Step 2. The request goes to the API server. The API server validates the request and accepts it. It also stores the desired state information in etcd. Step 3. The scheduler checks which pod needs a node. Then it chooses the best worker node for that pod. Step 4. The selected worker node receives the instruction. Kubelet on that worker node starts the pod. The container runtime pulls the image and runs the application container. Step 5. The pod starts running. Now the application is running inside Kubernetes. If the pod fails, Kubernetes can automatically create a new pod based on the desired state. This is the power of Kubernetes. Now let's look at some supporting components. The first supporting component is config map. A config map stores application configuration. For example, application settings, environment names, URLs, and non-sensitive configuration values can be stored in a config map. The second component is secret. A secret stores sensitive data. For example, database passwords, API keys, and tokens should be stored in secrets, not directly inside application code. The third component is persistent volume. A persistent volume provides storage for applications. By default, containers are temporary. If a container is deleted, its internal data can be lost. Persistent volumes help store data permanently, even if pods are restarted or recreated. Now let's quickly summarize the complete Kubernetes architecture. The control plane makes decisions and manages the cluster. The API server is the entry point. It stores cluster data. The scheduler chooses the best worker node. The controller manager maintains the desired state. The cloud controller manager handles cloud resources. Worker nodes run the actual applications. Kubelet runs and monitors pods. Kubeproxy handles service routing. The container runtime runs containers. Pods are the smallest deployable units. Services provide stable access to pods. Ingress provides entry into the cluster from outside. Config maps store configuration. Secrets store sensitive data. Persistent volumes provide storage. So the main idea is very simple. We tell Kubernetes what we want using YAML. Kubernetes accepts the request through the API server. It stores the desired state, schedules pods, runs containers on worker nodes, and continuously checks that everything is working as expected. That is how Kubernetes manages containers at scale. I hope this explanation helped you understand Kubernetes architecture clearly. Thanks for watching.